Bright Duty. Every student matters.
Hi dear students, I am Amit Ajmani, once again back with your gravitation chapter. Till now we have studied about the thrust and the upthrust, the buoyant force, the buoyancy, and how it basically exerted a particular force on an object. Today we will be studying about a very important topic from your syllabus, that is Archimedes principle. Now let us do an activity first of all to actually relate what Archimedes principle is going to say to us. Now we'll take a particular stone or an object and we'll tie a thread to it, right? Now we know that this particular stone has some weight. So because of that weight, there will be some tension in this particular string, this rope or string that is going to stretch. We can also take it attached to a spring balance in which we can see what exactly is the weight shown of this particular stone or object in the spring balance. Fine. Now what we'll do is we will try to just put this stone in a container filled with a liquid or water. Now we will observe what? We'll observe that the elongation of the string has decreased a bit, right? Or if it is attached to a spring balance, then we'll see that there will be a reduction shown in the weight through the spring balance. Why did it happen? We already have read and understood that thing, because when this particular object has been lowered down in water, this liquid exerts an upward force which is known as the upthrust, and that actually is responsible for its weight loss. This is a common observation. If you must have seen or observed that whenever we are swimming, we find that we have lost some weight, like we feel a bit weightless in water. Why is it so? Because when we are swimming in water, that water just puts some upthrust on us, because of which we have that kind of feeling. Similarly, if I am taking out some water in a bucket out of a well, when the bucket full of water is into the water, I feel that it is a bit light. But when I just pull it up, the moment it will come out of the water, I'll directly feel, spontaneously I'll feel that it has become it has become heavier. Why was it so? Again, the same reason, because when the bucket was in the water was exerting that upward force or upthrust. Now this experiment, now we are correlating it. How? Let us take a glass or a container full of water initially, right? So now when I will lower this stone or object in water, we will see that some of the water will flow out of the container. Why? Because this object has some area and volume, and this will also require some space, and the space that it requires, the water that was up to the edge or the brim of this container, it will flow down. Again, if we take a glass of water and we will just take it fully, it's the glass of water is totally full of water up to the brim. Now if I'll insert one finger into that, I'll see that some water will flow out. If I insert 2 or 3 and 4 fingers, I'll see more water is coming out. So what does it mean? It shows that when an object is fully or partially immersed in water, then it displaces some water, right? Now how much amount of water it will displace? That is what is being related here in Archimedes principle, right? We saw two things. One, whenever we will immerse an object in water, there will be some weight loss in the substance or the object being immersed in water because of the upthrust. Second thing will be that the water will be displaced. Archimedes observed, calculated, and gave his principle correlating both these things. in both the things, how he correlated? He said that when a body or an object is partially or fully immersed in a liquid or any fluid, then it experiences some upthrust or buoyant force, and that buoyant force is actually equal to the amount of weight of the fluid displaced by it. Now try to relate, please. Let us take a hypothetical situation that when I took this object and weighed it in the air, the weight was approximately, let us say, 60 grams. Right? So when I lowered it and then if I again reweigh it, I find that again a hypothetical value that now the weight is 50 grams. So there is a weight loss of 10 grams because of the upthrust, right? Second thing, when the water is flown out and I just collect this water and if I weigh it, surprisingly I'll find that exactly 10 grams of water is flown out of the container. This is what was proved by Archimedes. Let us verify Archimedes principle. So now verification of Archimedes principle, let us see how we are going to do it. We'll be requiring some material. What all will be required? Let us see. We'll be requiring a spring balance with 0 to 100 gram force readings. Then we'll take a glass topper about 50 grams and a brass weight of 50 grams. Then we'll take thin cotton thread and we'll take a overflow jar. Along with it, we'll take a wooden block and we'll take a pre-weighed beaker whose weight is 37 gram force and 250 cc beaker containing tap water. Right? Now the procedure, how we are going to verify it, let us see. First of all, we'll take a glass topper and tie it to a fine thread. Make a loop on the other end of the cotton thread. Right? Then take the spring balance and check the spring balance for any zero error and record it. For example, if there is a zero error in the spring balance, here we'll record it to be 4 gram force. Then we'll tie up and suspend the glass topper from the hook of the spring balance, read and record its weight in air. Whatever its weight is, we'll just note it down. For example, the observed weight of glass topper in this case is coming out to be 48 gram force. Then place an overflow jar on the wooden block and slowly pour in it tap water till the water just starts overflowing through its spout. At this moment, stop pouring the tap water. Right? Now, after some time, the water from spout stops overflowing. In this situation, the water in the overflow jar is at the verge, at the edge of overflowing. Now, what will I do is, I'll do my next step of the procedure. I'll place a clean and dry pre-weighed beaker under the spout of the overflow jar. The weight we have already seen, calculated, 37 gram force. Right? Now, I'll just gently lower the glass topper into the water in the overflow jar till it gets completely immersed. Now, when the glass topper goes underwater, the spring balance registers less weight because of the upthrust. We know that. Also at the same time, the water overflows through spout and collects in the measuring pre-weighed beaker. Right? So now, because of the stopper going inside, some water has been flown out. Now read and record. Now the next reading is 30 gram force. We'll note it down. Right? Now the pre-weighed beaker in which the overflow water was there, will weigh that beaker along with displaced water on the common compressor balance. We'll note down the reading which comes out to be 55 gram force. This is the weight which contains the displaced water too. Now, there are certain observations and calculations that we need to relate. What are these? Please try to relate. The zero error in spring balance. Now, students, you must be aware what zero error is. The spring balance should have the mark at 0, and if there is any change in that, if there is some error into that, for example, in this case, the mark was at 4 gram force rather than 0. So, whatever reading will be there we will just count these 4 gram force, we'll deduct it off in order to know the actual value, because rather than from 0, the reading or the weight has been calculated from 4. The observed weight of the glass topper in air, we have seen and observed and noted down, it was 48 gram force. So the corrected weight of glass topper in air should be equal to the observed weight minus the zero error, which comes out to be 48 gram force minus 4 gram force, which comes out to be 44. Now the weight of pre-weighed beaker was 37, as we have already seen, right? Observed weight of glass topper in water was 30 gram force. Now the corrected weight of glass topper in water, once again we need to relate the zero error, that was 4 gram force. So correcting it, we'll take the observed weight minus zero error. So the actual value comes out to be 30 gram force minus 4 gram force, thus comes out to be 26 gram force. Therefore, the apparent loss of weight, if I calculate, of the glass topper in water will be equal to corrected weight in air minus corrected weight in water. Now the corrected weight, we have already seen how to correct it, including the zero error, that was 44 gram force, and that of in water was 26 gram force. Taking the difference, that comes out to be 18 gram force, right? So this was the loss of weight of the glass topper as compared to when it was in air and when it was put in water. Now we will see the weight of the pre-weighed beaker and the displaced water, that was 55 gram force. The pre-weighed beaker, when it was empty, we have taken the notings that were 37 gram force. Then after doing the experiment, we saw that the amount of water displaced, the amount of water displaced was also added, and when it was noted down the value, then we saw it came out to be 55 gram force. So we will see how much is the amount of water displaced, and how we are going to calculate it. We can simply calculate it by deducting the final value and the initial value, the difference out of it, that came out to be 18 gram force. Now if you relate that the loss of weight of glass topper in water is equal to the weight of water displaced by the glass topper, and in both cases it was 18, right? If we repeat the above experiment by immersing the glass topper in any particular different medium like strongly salty water or the brass weight in tap water and strongly salty water, we will notice the same observation every time, that loss of weight of glass topper in salty water is equal to the weight of salty water displaced by the glass topper. Rather than taking the glass topper, if we take the brass weight, again we will see that the loss of weight of brass weight in water is equal to the weight of water displaced by the brass weight, right? Rather than taking it in a normal tap water, if I take it in salty water having different density, again the same observation I will find, that is the loss of weight of brass weight in salty water will be equal to the weight of salty water displaced by brass weight. So it is clear that weight of water displaced by the glass topper or brass weight in any of the waters, in normal tap water or salty water, it will always be equal to the apparent loss of weight of glass topper or brass weight in water. So this is what Archimedes principle said. So according to Archimedes principle, what we observed was that the weight of the water displaced by any particular substance when lowered into or immersed into it, that will be equal to the weight loss. So by this activity we can verify Archimedes principle, right? I hope that you would have understood this activity. You must have enjoyed it, right? And this is how we can verify and we can relate the Archimedes principle. Now students, this Archimedes principle is quite important because these has so many applications in our day-to-day life. For example, all the ships, all the submarines that are made they are based on this Archimedes principle only. Another use or application, this is very important question, state Archimedes principle and also state its few applications. Another application apart from the ships and submarines is that the hydrometers and lactometers. Now you know what are lactometers and hydrometers? The lactometers are those instruments which are used to check the purity of milk, right? Fine. So those lactometers are also based on Archimedes principle, right? And all the hydrometers, for example, the instruments, what are hydrometers? The instruments which are used for determining the density of various liquids, they are also based on Archimedes principle, right? So this is all about Archimedes principle. I hope you must have understood it properly and thoroughly. Fine. Question. You find your mass to be 42 kilograms on a weighing machine, right? We must have had this weight done at many places in our life. We must have tried it. Is your mass more or less than 42 kilograms? Now every time we look at our weights, we become happy or we become sad, whether it is we are gaining weight or we are losing weight. But the thing is actually that value correct? No. Why no? There is a slight difference between the actual value and the apparent value. And why is it so? Because we know that if we are standing on the weighing machine, then in that case, every medium, solid, liquid or gas, it exerts pressure. And that pressure is in the upward direction, because of which there will be a slight upthrust, which basically causes a slight difference in the weighing machine's value. Right? I'm not saying that you are gaining more weight out of that, but this is what exactly the fact is, that there is a slight variation to it. Fine? Got it? Let us see the next question. You have a bag of cotton and an iron bar, right? Each indicating a mass of 100 kilograms when measured on a weighing machine. In reality, one is heavier than other. Can you say which one is heavier and why? Now, for a layman, for a normal student, the question appears absurd that I have taken cotton 100 kilograms, I have taken iron 100 kilograms, both are 100 kilograms. Then how come one is heavier and one is lighter? But exactly this is what is being asked in the question, and this actually happens. You would like to know the reason why? Let us see. Now we are saying that there is a bag of cotton. Now because cotton has lesser density, so this 100 kilogram cotton bag will be occupying a lot of space. And because it is occupying a lot of space, that is why the surface area on which the air pressure, the thrust acts, it will be large, right? Whereas when we take an iron bar, this iron bar has a lot more density. It is quite dense as compared to cotton, so its surface area is quite small, because of which the upthrust acting on that small surface area will be less. And due to this, even though the iron bar and the bag of cotton are both of 100 kilograms, but we will find the iron bar to be heavier to carry. Got it? And why? The reason, because of the large surface area due to the lesser density of cotton and the smaller surface area due to the greater density of iron, which leads to the difference in the buoyant forces or upthrust acting on them.